So sixth chapter is the stability of linear feedback control system. And in this chapter, we are going to look at specifically, we started discussing the concept of stability in the last chapter when we discussed that if your poles of the transfer function are located, on the x-axis, on the y-axis of the S-plane, then how your system stability is going to be affected. So we are going to take the same discussion in this chapter, and then we are going to solve some problems. And the final chapter, the final topic in this chapter is what we call the Routh-Hurwitz Stability Criteria. So we are going to look at that, and we're going to see how we can use that criteria to find the value of the gain of a controller in a system, such that the system turns out to be a stable system or an unstable system. So once again, to review what we discussed last week, is stability depends upon the poles of the transfer function, where the poles of the transfer functions are located. That determine if your system is stable, unstable, or marginally stable. If the poles of the transfer function are located, all of the poles are located on the left-hand side of the S-plane. Again, that discussion. So this is your S-plane. And so this is your real axis, your negative real axis, your imaginary axis, and your negative imaginary axis. And if your poles are located, all of the poles are located on the left side of the imaginary axis, then for a bounded input, or without going into the bounded input, then your system is going to be stable. And what did we discuss? Why our system is going to be stable if our poles are located on the left side of the S-plane? What was the reason? Anybody remember that reason? What is the reason that if our poles of the transfer function are located on the left side of the S-plane, why our system is going to be considered as stable system? Say it again. I cannot hear you. Exactly right. So the transient response of the system is going to be an exponentially decreasing transient response. So if your input is a stable input, or what we call bounded input means that an input that when you are increasing the time value, the input is bounded between two limits, or two values like a sinusoidal value or a DC value. Those inputs are called bounded inputs. Whereas the inputs like a ramp input or parabolic input, they are not bounded input, they're unbounded inputs. So if the system is stable, and that stability is determined from what? From your transfer function, the poles of the transfer function. If poles of the transfer function, all of them are located in the left side of your S-plane, then our transient response is going to be decreasing, exponentially decreasing. And if your input is bounded input, then your output is also going to be bounded once the transient response is going to die out. So your output will always be stable for a bounded input. And those systems are the stable systems. The second bullet point, as you can see, if all the poles of the transfer function are in the left-hand side of the complex plane, then system will be stable for bounded input. Transient response will either be exponentially decreasing signal or an exponentially decreasing sinusoidal signal. Now, on the other hand, if any one of the pole, not all of them, if any one of the pole, any pole is located on the right-hand side of the S-plane, then our transient response is going to be increasing, exponentially increasing. That's the third bullet point. If any of the pole is on the right-hand side, the system will become unstable because the transient response is going to be exponentially increasing signal. Either it's going to be exponentially increasing or exponentially increasing sinusoid if you have complex conjugate poles on the right-hand side of the S-plane. So you have a stable, you have unstable, and the third one we discussed is you have marginally stable system. That is, you don't know if the output will be stable or unstable. It depends on the poles of the output. Marginally stable system if your poles are located on the y-axis or imaginary axis. So if you have complex conjugate pole, for example, then these complex conjugate poles are going to make the system unstable, marginally stable. Likewise, if you have poles on the y-axis at 0, then that's also going to make the system marginally stable. Now, the multiplicity of this pole should be 1. That is, you should not have multiple poles of the transfer function on the y-axis at the same point. It should be single poles on the y-axis from transfer function. For example, if your transfer function is Ts is equal to 5s plus 6 over s plus 5 and s minus 6, s plus 5, s plus 6, let's say. So you have only a single pole at s is equal to 0, and this system is going to be considered as a marginally stable system because it depends on the input. If the input is a step input, then the output is going to become unstable, and we're going to do the problem. But if the input is not a step input, it's a sinusoidal input, let's say, then the output is not going to be unstable. It is still going to be sinusoidal, and the transient response is going to die down. Or not, it's going to be sinusoidal with the offset, DC offset by the value, what you see over here, 1 over s. However, if your transfer function is a s square over here, so now you have 2 poles at s is equal to 0. In this case, irrespective if your input is bounded or not, your system is going to become unstable, even for the bounded input, because s square means that you have, from the transfer function, when you convert into time domain, you're going to have t function, basically, t times something. And that t function is going to keep on increasing as time will keep on increasing. So your poles that are on, from the transfer function, the poles that are on the y-axis, the multiplicity of those poles should be 1. There should not be multiple poles at the same point for the transfer function. If there are multiple poles from the transfer function, the system is going to become unstable, irrespective if your input is bounded input. So there are 2 conditions of instability. One condition is very clear, that any of the pole on the right-hand side, system is unstable. And the second condition is if you have multiple poles at the same point on the y-axis, the transfer function multiple poles. If the transfer function of feedback control system has a pole at origin s is equal to 0, a step input will produce 2 poles for the output ys at s is equal to 0, and this will result in an unstable output. So system is going to be marginally stable, but output is going to be unstable. If the transfer function has a complex conjugate pair of poles on the imaginary axis, a bounded sinusoidal input that will produce a pair of complex conjugate pole at the same point will also make it an unstable output. So again, the system is marginally stable for this point. I think we discussed it last week as well. So let's say you have a complex conjugate pole J2 and negative J2 from the transfer function. So the transfer function will have numerator divided by one of the factors is going to be s square plus 4. So that's going to result in s plus J2 and s minus J2, 2 pole. So if you have a system like this, and if you are exciting this system with an input, let's say a sine 2t. A sine 2t will produce 2 poles at J2 and negative J2. That means now you have multiple poles on the y-axis for y of t, and the output is going to become unstable. I think there's an example that we are going to do based on this. So the point is that anytime you have multiplicity of poles on the y-axis, the output is going to become unstable. If the bounded input does not produce a pole or poles at the same points on the y-axis or imaginary axis, the output will still be stable. And there's a last point. Anytime there's a multiplicity of pole on the imaginary axis, system will be unstable. So these are the conditions for the system to be stable, marginally stable, or unstable, and that you can identify from the poles of your transfer function. Let's look at the first example. Transfer function of a linear feedback system is given by this. Determine the output of the system for a unit step input. What type of stability does the system exhibit? Okay, so this is the transfer function. We know that this is s plus 4 over s, and s squared plus 2s plus 3. It's going to be what? 3 plus 1, so s plus 3, s minus 1, whatever. What is that? S plus 3, s plus 1. No, s minus, is it complex or not? What are the roots? 3 minus 1 is 2, so s plus complex conjugate? Yeah, or minus 1 plus 1. So s plus j 1.41 and 1 plus j. Okay, so it's a complex conjugate. I thought it was real. Anyways. Okay, so what type of stability do we have from this system, by the way? Of course, these two are on the left side because it's plus 1. So that when you calculate the root, it's going to be negative 1 plus j 1.4 and negative 1 minus j 1.4. So what type of stability we are expecting? Marginally stable system. Marginally stable system because you have s in the denominator, right? So if you draw the pole 0, this is called the pole 0 plot. So if you draw the pole 0 plot of this system, then you have at s is equal to 0, poles are drawn with x, s is equal to 0, and then s is equal to negative 1 plus j 1.4 and negative 1 minus j 1.4. So these are 3 poles. And then you have 1, 0, which is at s is equal to negative 4. And zeros are represented in general with O's. So let's say you have negative 4 over here. Since negative 1 is here, I'm going to keep negative 4 here. So if you took DSP with me before, then you remember we used to draw the pole 0 plot. It's the same thing, but it's the analog domain. And this is the 0, which is at s is equal to negative 4. So zeros are represented with O's. Let me make it 0 so it looks like it's 0. Zeros are represented by O's and poles are represented by cross. This is called the pole 0 plot of the system. Anytime a pole 0 plot is given to you, you can determine right away if the system is stable or unstable or marginally stable based upon where the poles are located. In this case, of course, since one of the pole is located at s is equal to 0, the system is marginally stable. Marginally stable due to one pole at s is equal to 0. Now we are exciting the system with RT is equal to UT. So once we excite the system with RT is equal to UT, what type of output we are expecting? Is stable, unstable? There are two types of output, either stable or unstable. It's going to be unstable. So you know right away, without even any solution, you should know that the output you're expecting is unstable, because the unit step is going to produce 1 over S, and then you already have one pole at S is equal to 0. So with the unit step, it's going to be another pole at S is equal to 0 for the output. And two poles on the y-axis will give you an unstable output. So even before you start solving it, you should know that you are expecting an unstable output. So if your result is incorrect, then you're going to go back and check why you're not getting what you should be getting. So let's go ahead and solve this. So my ys is equal to transfer function times rs. I have s plus 4 over s square plus 2s plus 3, and then rs is 1 over s. Let's go ahead and use residue function. So my numerator is 1, 4, 1, 4, and my denominator is, so I have s square and then multiplied by the whole thing. So I have s4 plus 2s cube plus 3s square. So s4 plus 2s cube plus 3s square, and then 0s, and then 0 s to the power 0, that is constant. So you make sure you have to use zeros for the power of s that are not present in the equation. So you have s4 plus 2s cube plus 3s square plus 0s plus 0. That's the equation from the highest power to the lowest power of s. And this is what you are going to get. The first two, we were expecting those two roots, and the seconds are s. All right, now I'm going to tell you how to read if you have the repeated roots in the denominator. Now you have repeated roots for p. You have 0 and 0. So if you have repeated roots, repeated roots means you have multiplicity of roots, basically. So many times the mistake that students make is that they write negative 0.556 over s minus 0, and plus 1.33 over s. So the first one is the least power, which is s to the power 1, and then the power is going to keep on increasing. If you have multiple poles or multiple roots at the same point, that means in your denominator you have that much power of the polynomial. In this case, we have s square, remember, right? So the first one is going to be s, the second one is going to be s square. If you have s cube, then the third one is going to be s cube, then s4, then s5. So that's how you're going to read it. So once you're writing this thing from the residue function, then you're going to write it right here. You're going to write it. Let me write down first. I can write down s first, and s. So I have negative 0.5566. Negative, what was that, 1? Let me put it here on this side so I can see it when I'm writing. Negative 0.56 over s, that's the first power, plus 1.33 over s squared, the second power, plus 0.278 plus j 0.275 over s plus 1 minus j 1.41, and then the complex conjugate of 0.278 plus minus j 0.275 over S plus 1 plus j 1.4. So that's I'm going to show you, and then I'm going to. So if you call help residue, okay, so here is it for the repeated pole, as you can see, -2 over S minus 2, 7 over S minus 2 square, 3 over S minus 1, blah, 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 right? So it starts with the lowest power. Let's see. So RPK right here. P is 2, 2, 1. So you have two values of 2 and then 1. So the first value has the power 1, S minus 2. The second value has the power 2. And then, of course, 1 is simple. So it starts with the lowest power of the factor, and then it keeps on increasing if you have multiple poles. So this is again something that I have seen many students make mistakes. So make sure you write it down, you understand it, that whenever you see in the RPK, whenever you see in the P that you have same poles, then the first pole will have power 1, the second pole will have power 2, the third pole will have power 3, and so on and so forth. But most of the time, students just put down. For example, in this case, when you see the pole to be, what was that, 2, 2, when you see that, most students just do this -2 over S minus 2 plus 7 over S minus 2. So they ignore the power and then just put the same one. But remember, anytime you have multiplicity of pole, you will have the increasing power. Yes? Yeah. Yeah, I'm going to show you, but there was another question, I guess, somewhere. No? Okay. How did I put roots? Okay, let me go. Here you go. So I have, let me move it down to show you. So I have S plus 4 in the numerator. So S is 1. So 1, 4. Oh, okay. Answer. So 0.2778 plus this, that's this factor, right? And this corresponds to this. So S minus this number, that's the root. This is the root. You are making a factor from the root. This, because you are doing S minus the factor. Sorry, S minus the root, right? So exactly. So S minus the root is going to become S plus 1 minus J 1.4. That's the root, and you're making a factor out of that root. Yes. The first, as I said, and anytime it's going to give you the values in P, the first value is going to have the smallest power of S. Then the second value is going to increase. So the first value is -0.556, corresponding to the third, and 1.33 corresponding to the fourth. So this fourth one is S square, and the numerator for that is this fourth one. Because you have to match the numerator and denominator. This is the numerator for this root, right? This is the numerator for this root. This is the numerator for this, which is the first power of S. So S minus 0. And this is the numerator for this, which is S minus 0 square. If this would be like, let's say, this would be 2, like it is showing you here, 2, 2, 1. If this would be 2, then as you can see, -2 over S minus 2, so -2 over S minus 2, 7 over S minus 2 square, and then 3 over S minus 1, right? Well, that's what I'm saying. It's going to start from the lowest, and then it's going to increase. There's a way that you can see that. I know. Yeah, I don't remember exactly. Yes. Okay. Okay. Where? I know there's a way. Let me see. Yeah. RP, K, comma, E. It's going to show you the power. Okay, let's see. I just remember that it starts with the lowest and go to the highest. That's all I remember. So RP, K, comma, E. All right, so that is going to show this is the first power, and second power. That's good. Thank you. And K, basically, we have not used K, but K is if you have improper fraction, then first you have to divide the numerator by the denominator, and then you have some residue left. That residue comes in K, basically. So far, we have all proper fractions. That's why K is always empty. Okay, guys. So once we have this, let's go ahead and finish this and then take a break. Then YT is going to be negative 0.56 UT. Oh, not T. Negative 0.56 UT. I'm going to keep this. All right, 1.33 over S square will simply be 1.33 T. And that's why the system is going to become unstable from this factor. This factor is going to make the system unstable because T is going to keep on increasing. And then we have complex. So remember when we did complex, what did we do? 2 times the magnitude of the numerator. So if we convert the numerator into magnitude and base, so absolute value of R is the magnitude of all R's and angle of phase, no angle. Angle of R times 180 by pi. Remember, R is my numerator. So the first one, I have 0.39. So let's say I'm just going to take 0.39, angle 44.7. So 0.39, 0.39 angle 44.7 degrees. So what was that? 2 times the magnitude of the numerator, which is 0.39. So it's going to be 0.78, right? 0.78 e to the power negative 80, so negative t, cosine of the frequency, which is 1.41, t plus the angle, which is 44.7 degrees. And remember, this is we discussed in chapter number 2 when we were discussing the Laplace transform pair. I added that pair in chapter number 2. So this is your final result. And of course, as we can see, this factor will make the output unstable, 1.33 T. The system itself was marginally stable, but since the input also produced one pole at S is equal to 0, so the multiplicity of pole become 2. Therefore, the output becomes unstable. Any question? Does it make sense? Does it make sense? Okay. All right, let's go ahead and take a break and then start at 10:30. Okay, guys. So let's see. This needs to be deleted. Next example. Transfer function of a linear feedback system is given by this function. Determine the output of the system for a unit step input. What type of stability does the system exhibit? So to find the stability of the system, of course, we are going to S square plus 9 is going to be S plus J3 and S minus J3, right? Minus J3. S square plus J3 square or minus J3 square, J square is going to be negative 1, so plus 9. Yeah, S plus J3 and S minus J3. All right, what type of stability do we have? It's marginally stable system because you have complex conjugate roots on the y-axis again. pole zero plot. J3, negative J3, and we have 1, 0 at S is equal to negative 4. So that is the pole zero plot of the system. System is marginally stable. Marginally stable due to a single pair of complex conjugate poles on the y-axis. All right, again we are exciting the system with the step input, and we have to calculate the output of the system. So again, ys is equal to ts times rs, s plus 4 over s square plus 9 times 1 over s. Let's do it. S plus 4, so 1 comma 4, and then s square plus 9 times s, so s cube plus 9s. So s cube, and there is no s square, so 0, 9s, and 0. And these are our, oops, what did you? I'm going to start with s, so you have 0.44 over s plus negative 0.22 plus j 1.67 over s minus j3, and the conjugate pole again, negative 0.22 minus j 0.167 over s plus j. 0.2778 or 278 rather, negative 143, negative 143.13. I'll use this one actually because it's a positive angle. 0.278, 143.1. Okay. So once we do y's of t, then it's going to be 0.44 ut plus 0.2778 times 2. So 0.27 is 54. 0.54. So I'm just going to write down 55. E to the power, well, it's going to be cosine. So e to the power negative 0t basically. So it's going to be 1. Let's don't have to do that. Cosine of 3 e minus 143.1. and that will be your result. Yes. So when we did the whole derivation, let me open that so that you guys can kind of review that. Chapter 2, we did the derivation. Let me open chapter 2 notes real quick. Notes, chapter 2. Okay. So let's see. We're doing something, and then we did the whole derivation. Maybe here, yeah. Partial fraction decomposition. So we had this transfer function, and then we had plus 125 this and minus. So we went ahead and then we wrote down how to get the partial fraction decomposition and all those things. So we came out with this negative j55.9 over s plus 125 minus j this and then this. Now inverse Laplace transform a e to the power negative t plus a conjugate e to the power negative a conjugate t. So we went ahead and a was negative j55.9. We plugged that in over here. And this a was 125 minus j this, so plugging it here. So then when we did the expansion using Euler's identity and everything, it came out to be 55.9 e to the power negative 125 t to 2 times cosine 22360 t minus 90 degree. Now we discussed that, where is it? That when we convert this thing into polar form, that's going to be 55.9 angle negative 90 degrees, right? So this is 55.9 angle negative 90. So that's coming from your numerator. And then cosine frequency of that, frequency is this 22360, and exponential 125t. So that's your exponential coefficient 125. So that's through the derivation, we had the cosine signal. We did not have the sine signal when we did the derivation. So we are taking the cosine signal as what we did the derivation. Now in this case, of course, cosine 90 became sine, so we converted that into sine for this problem. But from this result, we deduce that when we have this type of pair, a over s plus a conjugate over s plus a conjugate, then we can write down 2 times the magnitude of a e to the power negative alpha t, where a is alpha plus j omega n, cosine omega n t plus angle of a. So that's what we did. Let's see. What did you say? You're saying if you take this first? So this is the expansion right here. If you look at the expansion and if you follow the expansion, this is plus 90 right over here. That raised to e to the power j 90 using Euler's identity. So we did the whole derivation, and from that derivation we did use that result. Whole derivation is here basically. So that's what I've been using instead of doing the derivation. Again, you can do the second order system as well, what we discussed, omega n square over s square plus 2 zeta omega n s plus omega n square. You can always, whenever you have a second order system, you can always write that system in terms of those quantities. Figure out what omega n is, figure out what zeta is, write down in the standard form, and then use the pair in the transform table, write down the result. You can always do that as well. To me, this is partial fraction is there. We already know what will be the result. It's easier to do instead of figuring out how to form that equation. But you can do whichever way you want. Well, yeah, because I was trying to show you guys that although in the table, it is the sign is shown, but it is the same thing as we get when we do the partial fraction decomposition and all those things. Even though you see a cosine over there, but you can convert that cosine into sine, and you're gonna get the same form as what is given in the table. So that's what I was trying to show you. Yeah. Yes. If it's not complex conjugate, it's real root, then it's simply e to the power negative at, remember? So that becomes even simpler, right? Okay, so that's what we used over here basically for this pair right here. Okay, so this is our final result for this. And this system turned out to be a stable system because your output is not producing any more poles at the same point as J3 and negative J3. Your output is producing a pole at S is equal to 0 again. So you have 3 poles here on the y-axis, but they are not multiple poles at the same point. Therefore, the output is still stable. And the output in this case is going to be a cosine signal, sustained output, that is, a steady state output is going to be a cosine signal, which has an offset of 0.44 and the peak value of 0.55. Okay, so delete this slide. Let's look at this one now. Transfer function of a linear system is given by s plus 1 over s plus 1, s squared plus s plus 9, s plus 4, s plus 1, s plus j3, s minus j3. So we already know that the system is marginally stable system because 2 poles are on the y-axis. So this is also marginally stable. And now look at the input. Input is now a sinusoidal signal, 4 sine 3t. 4 sine 3t. What type of stability does the system exhibit? So again, without going into the solution, if you draw just the pole zero plot, you will know the stability. You have one pole here, you have one pair of poles here, J3, negative J3, you have negative 1. And then out, so it's a marginally stable system. And then the output is, the input signal is sine 3t, and sine 3t is going to produce one pole at J3 and one pole at negative J3. So now you have 2 poles at the complex conjugate points where you have the pole for the TS. So you can expect the output of the system to be unstable. The system is marginally stable, but the output is going to be unstable. So again, make sure you understand this before you start solving the problem, so that if you make a mistake, you can always go and check your work. Yes? The second pole comes from the input, 4 sine 3t. Sine 3t in the Laplace domain is going to produce complex conjugate poles at the frequency. So 3, basically J3 and negative J3. If you go to the Laplace table, let's go, maybe this might not be there. Let me see if sine right here. So sine omega t, showing sine omega t, omega over s squared plus. So it's a variation of sine omega t. we can always multiply that by omega on top. So we can multiply this 4 sine omega t, so we can multiply that by omega, but as you can see, you're gonna have s square plus omega square. So s square plus omega is 3, s square plus 3 square. That's going to, 3 square is 9, so that's going to be the same as this, s square plus 9, right? Numerator is a constant value, so don't worry about the numerator. Numerator is omega, so remember you can always multiply and divide by the numerator to bring it in the same form. So that's not an issue. The important thing is this frequency. So sine 3t is going to be 3 over s square plus 9, right? We are given 4 sine 3t, so it's going to be 4 times 3 over s square plus 9. So 12 over s square plus 9, but it's going to produce another pair of poles on the complex conjugate plane at positive j3 and negative j3. Okay, so let's go ahead and solve this thing and see the output is unstable or not. Now, one of the pairs that we are going to discuss here is not in the table in the book, but it's online available, so we can add that pair in our table as well. So y of s is piece of s horse of s. And then 4 sine omega t, as we discussed, is 4 times 3 over s square plus 9. Sine 3t is 3 over s square plus 3 square. So 12s plus 4. All right, let's look at now residue function. So my numerator is 12, 48. Let's say 12, 48. And 12, 48. And my denominator. So I have one root. I can create a polynomial from that. So I'll show you how to create a polynomial if you know the roots. So the function is poly. If you know the roots, you can create a polynomial using the function poly. Since we already know the roots, instead of multiplying them and all those, I'll just let MATLAB calculate the polynomial. One of my roots, the first one is -1. The second and third root, negative j3, positive j3, and then negative j3, positive j3. So negative 3i, 3i, and then negative 3i and 3i. So these are all my roots. And once you put roots and use the function poly, it's going to create the polynomial, coefficients of polynomial from those roots. And I'm going to put apostrophe because it creates a column vector. Actually, let me just show you. If you don't put apostrophe and try to do it, it still works. So apostrophe or without apostrophe doesn't really matter. So these are my R and P. And again, you can see multiplicity of the roots. That's going to be the first power. That's going to be the second power. Again, first power and second power. Let me move this so I can write down my partial fraction. Okay, first I'm going to write down my S. So I have 0.36 over S plus 1, which is this function, this vector right here. And then I'm going to write down the first let's write down the first pair. So I have, let me just write down this first. Negative 0.18 minus j 0.20 over s minus j3 plus negative 0.18 plus j 0.204 s plus j3. Okay. And now I'm going to write down the second power of positive j3 and negative j3. So I have negative plus negative 0.43 plus j 0.3 and s minus j3 square, and I have now plus negative 0.43 minus j 0.3 s plus j3 square. Yeah, so this is what I have. Right. S plus j3 square and s minus j3. Okay. Let me go ahead and do absolute value of r, angle of r times 180 by that's my 0.27 angle negative 131 degrees, 0.27 positive 131 degrees, and this is going to be 0.52, 53 angle 145 degrees, and 0.53 angle negative 145 degrees. All right, the first one and the second pair is easy. Now this, with the denominator s plus j3 square, this is not in the table in the book, but if you search online, then you can find 1 over s plus a square is t e to the power negative alpha t. The seventh pair, sixth pair, t e to the power negative alpha t, 1 over s plus a square. Let's go to the next page. So if calculate yt. Let's see if I can calculate it correctly. So the first one, of course, is e to the power negative 0.36. 0.36 e to the power negative t. The second and third pair is going to create a cosine signal. 0.27 times 2, 0.54. Cosine e to the power 0.54 e to the power 0t, so e to the power 1 cosine 3t minus 131 degrees plus, okay, let's look at this pair now. So we have 0.53 angle 145. So let's 0.53 angle 145 we can write down e to the power negative 145 negative 145 degrees, positive 145 e to the power 145 degrees. So remember we discussed that 0.53 e to the power 145 using Euler's identity, e to the power x and e to the power negative x cosine x e to the power jx, sorry, not just 145, j145, j145. E to the power jx is cosine x plus j sine x, and e to the power negative jx is equal to cosine x minus j sine x. So when you do e to the power jx plus e to the power negative jx, we're going to get 2 cosine x and cosine x, or jx plus e to the power negative jx over 2. So that's your Euler's identity. And when you do e to the power j145, e to the power j145, that's going to be cosine of 145 plus j sine of 145, and this is a rectangular coordinate. You convert it into polar form, cosine square 145 plus sine square 145, the magnitude is going to be 1. Cosine square x plus sine square x, magnitude is 1. And the phase is going to be arctan of y over x. So sine 145 over cosine 145, 1 tangent inverse of tangent of 145. So this tangent inverse is cancelled out, and it's going to come out to be 1 angle 145 degrees. So that's why anytime you, in the polar form, you are given x angle something, you can write down x e to the power j that angle. And that's why I wrote down that over here. We did that in chapter 2 as well. And then s minus j3 is square. So s minus j3 is square according to the table. Let me see, let me check the table again. 1 over s plus a square is t e to the power negative alpha t. So that's going to become, so here s plus a is square. So a here is negative. You're saying something? A here is j3 and a here is positive j3. So t e to the power negative alpha t, t e to the power negative j3 t plus 0.53 e to the power negative j 145 degrees t e to the power j negative, I'm sorry, which alpha you're referring to? Right, this is A. So again, if you look at this pair, 1 over s plus a is square is t e to the power negative at. Yeah, so I'm using this pair. 1 over s plus a is square t e to the power negative at. So 0.53 e to the power negative j 145 degrees t e to the power negative j 13t. And now we can combine them. Don't expect me to give you this type of question, by the way. This is just to show you that why that sinusoidal signal is creating an unstable output, but I'm not going to give you a signal like this or system like this in exam for sure. Homework maybe, but not in exam. Okay, 0.53 is a common factor. T is common. And then we have e to the power j3. And I'm just going to write down j 3t plus 145 degrees. And from here, e to the power negative 3t plus 145 degrees. So the last one is going to make another cosine signal right here, ejx plus e to the power negative jx, 2 cosine x. So this is going to be 2 times cosine 3t plus 145 degrees. So 2 times 0.53 is going to be 1.06, right? 1.06 t cosine 3t plus 145 degrees. And that is your final result. Again, you don't have to do the whole derivation. Once you do it once, then you can always relate it that if your pair is 1 over s plus a square, then how the output is going to look like we did for the sinusoidal signal. But because of this, output is unstable. T is going to keep on increasing linearly, which will make the output to be unstable. So once again, system was marginally stable with complex conjugate roots on complex conjugate poles on 3t, J3 and positive J3. And the input was a sinusoidal signal with 3 radian per second frequency that will make another complex conjugate pole at 3 and J3 and negative J3. And that resulted in the unstable output. So understanding is important, guys. It's possible I'll give you a question and I can ask you, you don't have to do any derivation or anything, just by the location of poles. If the input is this, answer with logical reason as why the output will be stable, unstable, marginally stable, whatever. Why the system is stable, unstable, marginally stable. And if this is the output, what will be the status of the, if this is the input, what will be the output, stable, unstable. Output can only be stable, unstable, of course. System can be unstable, stable, or marginally stable. So many times it's just I'm looking for the understanding, not the whole math or derivation. So make sure you understand it. Okay, so that wraps up the discussion and the problems for the first topic, as where you have the poles located for the transfer function. And we started that last week. And then how the system is going to behave as far as stability is concerned, and for what type of input the output is going to become stable or unstable. The last topic, which is the main topic of this chapter, is Routh-Hurwitz Stability Criteria. So as you can read, the first bullet point, back in 1800s, Hurwitz and Routh, they independently published a method of investigating stability of linear system based on the characteristic equation of the system. Characteristic equation is what? Characteristic equation is the denominator of the transfer function. That's the denominator of the transfer function is called the characteristic equation of the system. Denominator polynomial of the transfer function. Now back in 1800s, there were no computers. They did not have the luxury of finding roots, but just typing roots. Now we can do that. So we know exactly what is located where. They had to go through all these things that you're gonna see in order to just figure out, even for the easiest of the system, if it is stable or unstable. Now we can easily find out the location of poles, and we can determine if the system is stable, unstable, or so. That's not the point now for using this method. The point now for using this method is, in general, that if you are creating a control system and you're trying to figure out, you have a controller gain or something, and you're trying to figure out, hey, what is the range of the controller gain for which my system will be stable? Under those conditions that you're trying to figure out that value, unknown value, you can use this method to figure out, oh, the value of gain can range from 1 to 10, and if it goes beyond 10, the system is going to become unstable. Because if it is just to know the stability of the system, you can easily put roots and the polynomial, the denominator, and you will see if the roots are located on the right side of the plane, unstable, left side of the plane, stable, on the axis, marginally stable. So again, at that time, even calculating a root of a fifth order system, was a challenge for most of the people. So they could do it using this method just to figure out if the system is stable or unstable. But now, as I said, our the way we use it is we use it to figure out range of gain and all those things using this method, not just if it's stable or unstable stuff. So as I said, 1800 without any computers, relatively hard to figure out roots of a polynomial with high power. Therefore, it was sometimes cumbersome to determine where the roots would be located to determine the stability of the system. Routh-Hurwitz method was of utmost importance under those situations. And now we can just use MATLAB to do that. It still come handy to determine the value or range of a gain parameter in a control system that will result in a stable or an unstable system. So how does the system operate? Characteristic equation, that is the denominator of the transfer function. General polynomial we can write down, an sn plus an minus 1, sn minus 1, a1 s plus a0. So just the general parameters. Two necessary conditions for the system not to become unstable. All coefficient of power s must be non-zero. So all coefficients of powers of s must be non-zero. an minus 1, a1, a0 must be non-zero. All coefficients of power of s must have the same sign. Either all of them are positive or all of them are negative. So these are, first of all, necessary condition for the system not to become unstable. If you don't have one of those conditions, that does not mean the system is unstable, though. You have to go and check a little more. You have to investigate a little more. It's possible the system is still stable. But at least you should have those two conditions to say that, well, at least the system is not unstable. If any of these conditions are not satisfied, the system will become unstable. And sometimes you will see that. If both conditions are satisfied, further investigation will be required to determine about the stability of the system. As I said, if both of the conditions are satisfied, then you still have to further investigate if the system is stable or unstable. But if they're not satisfied, any condition, then the system is going to be unstable. To determine the stability of a linear system through Routh-Hurwitz, first we create the array of the characteristic equation and then investigate from that array. So how do you create an array? This is how you create an array of Routh-Hurwitz. So if your characteristic equation, generic characteristic equation is given like this, then on the left-hand column, you write down all the powers of S from the highest power to the constant, which is the 0 power. And then the first two lines, you start with the highest coefficient, and then you skip one, go to the next one, you skip one, go to the next one, and so on and so forth. And the second line, you start with the second coefficient, you skip one, write down the next one, and then you skip one, write down so the first two lines are coming from the characteristic equations. And then the third and the subsequent lines, you have to calculate the values. So how do you calculate these values? Bn minus 1, Bn minus 3, Bn minus 5, Cn minus 1, Cn minus 3. So Bn minus 1 is negative 1 over An minus 1, negative 1 over this value, and the determinant of the first column and the second column. Bn minus 3, again negative 1 over An minus 1, and the determinant of the first column and the third column. And likewise, you can keep on going. Bn minus 5, negative 1 over An minus 1, determinant of the first column, and then you will have the fourth column. And likewise, Cn minus 1, negative 1 over Bn minus 1, determinant of the first column, An minus 1 and Bn, the second line and third line, the first column, and the second column. And likewise, Cn minus 3 is going to be negative 1 over Bn minus 1, determinant of the first column and the third column. So this is how we calculate those Bn and Cns and all those things. So just to give you an example, if my characteristic equation, and we represent characteristic equation by Q of S. If my characteristic equation is S5 plus 6S4 plus 7S cubed plus 6S squared plus 8S plus 9. Let's say this is the denominator of my transfer function. So if I'm creating a Routh-Hurwitz array, then on the left-hand side of this, I'm going to write down S5, S4, S cubed, S squared, S to the power 1, and S to the power 0. And then the first row is going to be starting with the coefficient of the first term, S of 5. So 1, then S cubed, 7, and then S, 8. And then the second line is going to be the coefficient of S4, which is 6, and then S squared, which is 6, and then S to the power 0, which is 9. So these will be my first two rows, and they come from the characteristic equation. And now to calculate the row for S3, S cubed, I have Bn minus 1. Usually I just write down B3, B1, and okay, so let me so Bnn is 5. So let's say 5 minus 1 is 4. So let's say this is B4. B4, and then Bn minus 3. 5 minus 3 is 2. B2, and then B0. Let's do this. That's easier. And then Cn minus 1 C4, C2, and then C0, and then D4, D2. And some of these terms are going to be 0, so you don't have to worry about those. E4, E2, E0. So B4, let me do it here. So B4 is going to be negative 1 over 6, negative 1 over an minus 1. An minus 1 is this. So negative 1 over 6, and your determinant of 1 and 6, an and an minus 1, and an minus 2 and an minus 3. So 7 and 6. So that's going to give us what? 1 times 6 is 6, 7 times 6 is 42, right? Divided by negative 6. So 42 minus 6 over 6. What is 42 minus 6? 36. 36, right? So 36 over 6 or 6. So this is going to be, B4 is going to be 6. B2, similarly, negative 1 over 6, and the determinant of 1, 6, 1, 6, and then an minus 4, an minus 5. An minus 4, an minus 5, which is 8 and 9. 8 and 9. And this will give us 9 minus 48, or 48 minus 9 over 6. 48 minus 9 over 6. I just multiplied by a negative sign. So 48 minus 9 is going to be what? 39. 39 plus 9 is 48. 39 over 6. So that's going to be 39 over 6. And B naught is going to be most likely 0. So B naught will be negative 1 over 6, the first column, and then now you don't have any column over here. We have already used an minus 4, an minus 5, so you don't really have anything here. So that's going to be 0, 0, which will be 0. So this will be 0. And similarly, you're going to calculate C4, C2. In this case, C4 is going to be negative 1 over 6, and the determinant of 6 and 6, and 6 and 39 over 5. And then C2 is going to be negative 1 over 6, and the determinant of 6 and 6, and 9 and 0. And C naught will be 0. And likewise, B4 is going to be negative 1 over C4, determinant of B4 and C4, and B2 and C2. And then D2 is going to be determinant of negative 1 over C4, determinant of B4 and C4, and then B naught and C naught, that will be 0, so D2 will be 0. And then again, you can only have E4 over here, and rest will be 0. So this is how you calculate the matrix, right? This is just the method I'm telling you how you're going to calculate it. The use, we're going to see, well, what's the use of doing this. So that's how you're going calculating each value, starting from the third line all the way up to the sixth line. The first two, they are coming from your characteristic equation. Any question about? Yes. So B2 is this 5 minus 3, right? So negative 1 over an minus 1. An minus 1 is 6. So negative 1 over 6, and the determinant of an minus 1, which is 1 and 6, an and an minus 1, and an minus 4, an minus 5. An minus 4 is 8, and an minus 5 is 9. So let me write this down. This is an minus 1, an minus 2, and an minus 4. And this is an minus 1, an minus 3, and an minus 1. N is, of course, the highest power, which is 5. So A5, A cube, A to the power 1, and A2, A4, A2, and A to the power 0. Or A0, not A to the power 0, A0. All right, so once we know how to create the matrix or array for Routh-Hurwitz, let's see how we can use it. Let's go to the next slide. If real part of any root of the characteristic equation is positive, the first column of the Routh-Hurwitz will have that many sign changes. For example, if real part of two roots are s is equal to 3 and s is equal to 7, there will be two sign changes in the first column of the array. Therefore, any sign change in the first column of the array will result in the system to be unstable. So one of the conditions is, once you create the array, if you have any sign change in the first column from positive to negative or negative to positive, the system is going to be unstable. And again, we don't really have to create the system to know that there's unstable or not unstable, because we can always find the roots of the characteristic equation, right? But again, back in the days, imagine when it was hard to find the root of 5th order, 6th order, 7th order system. You can create a matrix and you can see if there is any sign change in the first column, and the number of sign changes mean that many poles are going to be on the right hand side of the S-plane. If you have two sign changes, you have two poles on the right hand side of the S-plane. If you have one sign change, one pole in the right hand side of the S-plane. So the system is going to be stable as soon as you have a sign change in the first column, the system is unstable. So that's what it is. Basically, the first point is here. Therefore, for a stable system, there should not be any sign change in the first column of the array. Either all of them are positive or all of them are negative in the first column. 4 different cases: no zero element in the first column, a 0 in the first column but other elements of that row are non-zero, a 0 in the first column and other element of that row are also 0, and then repeated roots on the imaginary axis. The last one, it does not really do a good job when you have repeated roots at the imaginary axis. That is, if you have unstable system because you have multiplicity of roots on the imaginary axis, it does not detect that properly. But the first one, second one, and third one, there are cases that it can detect. What type of systems is that? What is the stability of the system? All right, so let's look at that. No 0 in the first column, we will create the Routh-Hurwitz, and if there is any sign change in the first column, system will be unstable, or else it is going to be stable. All right, what is given to us? The create Routh's array for the following characteristic equation and determine if the system is stable or unstable. So let's do that and then see if it is stable or unstable. And again, if you want to know if it is stable or unstable, just find the roots of this equation and see if all the roots are on the left side, right side, whatever, and you will know the stability. But using the Routh's array, s cube, s square, s to the power 0, 1 and 2, 1 and 24. This is Bn minus 1, n is 3, so B2 and B0, and then C2 and C0. B2 is negative 1 over 1, so it's just basically negative 1. Determinant of 1, 1, 2, 24, which will give us 24 minus 2 22. And B naught is, again, -1, determinant of 1, 1, and 0, 0, which will give us 0. So, oh, this is going to be -22. 24 minus 2, and then there's a negative sign over here, negative. So that's -22 and 0. So the sign has changed. So we know that the system is unstable. The system is unstable. The question is, how many roots are there in the right-hand plane? We know at least one root is in the right-hand plane because one sign changed. Let's see if there's another sign change by calculating C2. So C2 is -1 over B2, -22, 1 B2, so 1, -22, and 24 B naught, 24 and 0. So 0 and 1 over 22, and that's going to be 24 times 22. 0 minus -22 times 24. So C2 is going to be 24. So there are two sign changes in the first column. First sign change is from positive to negative, 1 to -22. And the second sign change is from -2 to +24. Now, anytime you have one sign change, your system is unstable. So if we find the roots of this quadratic equation, (1, 1, 2, 24). You have -3, which is on the left-hand side of the S-plane, and then you have two complex conjugate roots on the right-hand side of the plane. So the system is unstable because of these two complex conjugate roots, which are on the right-hand side of the S-plane. And that's what the Routh-Hurwitz criteria told us, that the system is unstable because you have a sign change, and there are two sign changes, positive to negative and negative to positive. That means there are two roots in the right hand. Right? And again, as I said, we don't really have to create this array to figure out the stability. We just use the roots function, and we know that the system is unstable because roots function is going to give you. So if it is, again, that's another thing. If it is just required, if I just ask you in the quiz, in the exam, determine the stability of the system, right, from the transfer function. So all you have to do is to take the denominator of the transfer function, characteristic equation, see where the roots are located using the roots function, and then determine the stability of the system. You don't have to create Routh-Hurwitz array or anything else. I've seen a student creating Routh-Hurwitz array just to determine if the system is stable or not. You don't need to do that unless it is being asked, hey, use Routh-Hurwitz array to do this. Then you can use it. But if somebody asks me if the system is stable or not, I'm not going to go through all this. I'm just going to calculate the roots of that and then determine the stability of the system. So this is how we are going to calculate all the values, as you can see. Okay. 0 in the first column, but other elements of the row are non-zero. We create roots array and replace the 0 in the first column by a small positive number represented by epsilon, and then complete the array. And then we determine if the system is stable or unstable. So let's look at this example. S5, S4, S cube, S square, S, and S to the power 0. So you have 1, 2, 1, 2, 11. and then you have 2, 4, 10. 2, 4. And then you have Bn minus 1, so B4, B2, B0, C4, C2, C0 is going to be 0 most likely, and then D4, D2 is going to be 0 most likely. I'm just going to write down, and I'm going to write down C0, D0, but those going to be 0, and E4, E2. We don't have to calculate all of them because some of them will be 0. So when we calculate B4, that's going to be -1 over 2, -1 over this, and the determinant of 1, 2, and 2, 4. 1, 2, 2, 4. Which will give us a 4 minus 4. So that's going to give us 0. Okay, let's calculate B2. -1 over 2, 1, 2, and then 11, 10. So 10 times 22, 10 minus 22 over -2. So 22 minus 10 is 12. 12 divided by 2 is 6. That's going to be 6. And B naught is going to be 0 because you don't have any column over here. This is all 0. So this column will be 0. Therefore, B naught is going to be 0. Okay, now since this is 0, you cannot really calculate C4 because C4 will be -1 over the first element of the last row. So if we do -1 over 0, that's not going to work. So that's what we have to do. If the first element is 0 and the other elements are non-zero, again, you don't have to worry about this because this whole column is 0, therefore B naught does not even exist. So you can just eliminate B naught. But B2 is non-zero, B2 is 6. So if your B2 is 6, what you're going to do, you're going to assume this to be a non-zero entity, a very small number, replace that by epsilon. So we assume that this thing is epsilon. And then it's going to become -1 over epsilon. And you're going to have 2 epsilon. No, sorry. Yeah, 2 epsilon 4, 6. So that's going to be 2 times 6, 12 minus 4 epsilon over negative epsilon. All right, so remember, epsilon is a very small number, right? So let's say 0.1. Although 0.1 is a large number, but let's assume 0.1. So if it is 0.1, then of course this C4 is going to be a negative value. 12 minus 0.4 over negative 0.1. So that's going to become a negative value. So C4 is going to be a negative value. Right? We can calculate C2 irrespective. C2 is -1 over epsilon, 2 epsilon, and then C2. So we have 2 epsilon, and what did we have? 4, 6 or 10, 0. 10, 0. So that's going to give us 2 times 0 is 0, 10 times epsilon. So that's going to give us 10. 10 times epsilon divided by epsilon. So C2 is 10. Doesn't really matter. D4. So we already know that the system is unstable because if we assume epsilon to be a very small positive number, then it changed from positive to negative. The system is unstable. We already know that. How many roots? You can again figure out if D4 is changing, it's becoming positive again, then it's going to be 2 roots in the right-hand plane. If it is not, then it's going to be 1 root in the right-hand plane. So you can keep on going and you can figure that out. So D4, we can just do that just to see if it is positive or negative. D4 is going to be negative 1 over C4. That's a negative number. So, let's say negative 1 over any negative number. Let's say negative 5 or something, whatever the number is. Negative number. And then we have epsilon, negative 5, and 610. This will give us 10 epsilon plus 10 epsilon plus 30 divided by 5. So this is a positive number. So this D4 turned out to be a positive number. That means you have 2 sign changes already. So you have a couple of complex conjugate roots on the right-hand side. And then you can find out E4, that's going to be again positive number most likely. So let's go ahead and see roots. S5, 2S4, 2S cube, 4S square, 11S, and 10. So the first 2 roots that you can see, they are on the right-hand side, 0.895 plus 1.4j, and so they are complex conjugate pair on the right-hand side, which will make the system unstable. The last 3 roots are on the left-hand side. But even if you have 1 root on the right-hand side, the system is going to become unstable. So 2 sign changes, you have 2 roots on the right-hand side, system is unstable. So if you have, again, a 0 in the first column, but the other elements in that row where the 0 is are non-zero, then take epsilon and solve rest of the array to figure out if the system is stable or unstable. Once again, we don't really need to do that if the matter is just to find stability or instability. Zero in the first column and other elements of the row are also 0. In this case, either all elements of a row are 0 or the only element in the row is in the first column is 0. If all elements of a row are 0, the system will either be unstable or marginally stable. For an unstable system, the roots will be of the type S plus alpha and S minus alpha. And for a marginally stable system, roots will be complex conjugate on the imaginary plane, S plus j omega, S minus j omega. The roots can be figured out from auxiliary polynomial US, which precedes the row that is all 0. Let's see if we have an example. Okay, let's do this thing. Create roots array for the following characteristic equation. And determine the stability of the system. Oh, this is different. Let me see. I have a different. Let's see. I think I'm missing a slide here. Okay. I think I'm missing a slide. Let me see. Yeah, this is example 6.7. I think I added one more slide last time. Let me do it. So let me go and add a slide here. So, slide. All right. And that's going to be example 6.6. determine the stability of the following system. Using and the characteristic equation of the system is S5 plus 6S4 plus 73S cubed plus 274S squared plus 1332S plus 2088. So let's create the Routh-Hurwitz array. S5, S4, S cubed, S square, S without 0. 173, 1332. And then 6, 274, 208. Those are our first two rows. And then this is going to be n minus 1, so B4, B2, B0, C4, C2, C0, B4, D2, B0. All right, some of them will be 0. We already know which will be 0. In this case, B0 is going to be 0 because you don't have any column over here. Of course, C0 will not even exist if B0 is 0. So we can just delete this, and D0 is not going to exist. D2 is going to be 0 because again this is 0. And then E2 and E0 will not exist, of course. So D2, E2, E0, all three of them they're not going to exist because that's 0. Okay, so let's look at B4. Negative 1 over 6, determinant of 1, 6, 73, 274. And let's see, I have already solved it. It's 82 over 3. 1 times 274 minus 73 times 6 divided by negative 6. So B4 is 82 over 3. B4 is negative 1 over 6, 1 over, not 1 over 6, 1, 6. And then the third row, 1332, 2088. And this is coming out to be 984. So these are both positive quantities. So far, so good. Two over 3 and 984. And of course, this is going to be 0 because our second row is going to be 0, 0. Now my C4 is negative 1 over 82 by 3, so negative 3 over 82, and 6, 82 by 3, and 274 and 984. 274 and 984. Let's see, I'm getting 58. And of course, C2, since this is 0, C2 is negative 3 over 82, 6, 82 over 3, and 2088 and 0. 2088 and 0, which will give me 6 times 0 is 0, then negative 2088 times 82 by 3 times 82 over 3 divided by negative times, or divided by times negative 3 over 82. So that's simply going to give me positive 2088. So far everything is good. 2088. All positive in the first column. Now when we do T4, that's where the problem is going to be. T4 will be equal to negative 1 over 58 and 82 over 3, 58. And then 984 and 2088. 984 and 2088. And when you do this, you are going to get 0. Let me confirm this, because I've done it before, but let's just confirm it real quick. So D4 is equal to 82 by 3, 82 by 3 times 2088 minus 984 times 58. So that's coming out to be 0. So D4 is coming out to be 0. And D4 is coming out to be 0, and D2 is going to be 0 because you have 0 and then 0. So this whole column, the second column, is going to be 0. So D2 is going to be 0 as well. So now we have a situation where the first element of the column, first column is 0, and the other elements are 0, or the other elements do not exist. The only element that exists is the first element. In this case, that's the case. The only element exists. First element, the second element is 0 because this is 0 and this is 0 as well. Nothing. So now there is a situation. We cannot do E4. It's going to be 0, even if we assume D4 to be an epsilon value. So under this condition, we know that the system is going to be either marginally stable system or unstable system. If you have the first value of the column 0, and all the other values in that row are either 0 or there is no other value. The first value is the only value. If you have that condition, then your system will either going to be marginally stable or unstable. How are you going to figure that out? You're going to go to the previous row where you have the 0. You're going to go to the previous row, S square in this case, and you're going to create a polynomial out of that. So you're going to create 58s square plus 2088, and then solve this to find the value of S. If the value of S is complex conjugate that lies on the y-axis, the system is marginally stable. And if S returns two values, real values, one positive, one negative, or both positive, then the system is going to be an unstable system. So for this case, we have S is equal to square root of 2088 over 58 plus minus. Sorry, S is equal to negative 2088 over 58, which is complex conjugate number 58. So 6. So S is equal to plus minus J6. So that will make the system to have two poles at 6, J6 and negative J6, and the system is going to be a marginally stable system. If this comes out to be positive 6 or negative 6 or any value that is on the real axis, but one of those values is on the right-hand plane, then the system is going to be an unstable system. In this case, system is a marginally stable system. And again, you can use the Routh's function. Yes, go ahead. C4 is not 0. Yeah. So if C4 is 0 and C2 is still a positive number, oh, then if that, so that's not going to happen because, yeah, you can use the previous one. You can have 3 roots then. And out of those 3 roots, then 2 are either going to be on the y-axis or some roots are going to be in the right-hand plane. So you're going to go to the previous equation. But generally, when this is going to happen, either it's going to happen when the power is s, so that you have s square, or it is going to happen in s cube, so that you can have an equation s4. So generally, that's when it happens. It does not really happen with s square, so that you have to make that question with s cube. I have not seen that too in all the problems that we have. But if it does happen, then yes, you're going to go to s cube then. Then you're going to create an equation. In this case, you're going to create an equation b4s cube plus b2s is equal to 0. So that's going to be s is equal to 0. That's going to be one root. That makes it automatically marginally stable system because s is equal to 0. And then s square, what is that going to be? 82 over 3 s square plus 984 in that case. So one root is going to be at s is equal to 0, and then from the quadratic equation, you're going to find out where the other 2 roots are. If any of those roots are in the right-hand plane, the system is unstable. So remember, unstable takes the priority over marginally stable system. If your roots are on the y-axis, but any root is in the right-hand plane, then you're not going to write the system is marginally stable. The system is unstable because marginally stable is gone if you have at least one root in the right-hand plane. All right, now we're gonna do a real problem. We can take a few minute break maybe and then do a problem. By the way, this chapter part of exam next week or no? Okay, so we can finish it later on. That should be a problem. It's not that much left anyways. Should be able to finish today. Just quickly, let's see what are the roots of that quadratic, that polynomial, just to see if we have those roots. 1, 6, 73, 274, 1332, and 2088. So the first 2 that you can see, positive J6 and negative J6, and then the rest of the roots, they are in the left-hand plane. So the first 2 roots make the system a marginally stable system. All right, let's go ahead and take another short break and then continue from here. It's 11:59, maybe about 5-minute break, and then see if we can finish this chapter. If not, that's fine. So the next example, create Routh-Hurwitz array for the following characteristic equation and determine the stability of the system. So this type of example now it will be useful to use Routh-Hurwitz because we need to find out the range of k for which this system is going to become stable. It's not explained in the, I should have explained it properly, that what exactly we are doing. But we are trying to figure out the range of k for which this system is going to be a stable system. So when we have to do that, then Routh-Hurwitz come pretty handy. So let's go ahead and create the array S cube, S square, S to the power 0, 1 and 4, 2 and K. And then we have, let's see, we have 3 minus 1, so B2, B0, that will be 0, and then C2. So B2 will be equal to -1 over 2, determinant of 1, 2, and 4K. 1, 2, and 4. Which will give us K minus 8 over -2. So 8 minus K over 2, or 4 minus K over 2. Oh, we can just keep 8 minus K over 2. That's okay. So that's our B2. And B0 is going to be 0 because you don't have any column over here. So that's 0, 0. So that's going to be 0. And C2 will simply be -1 over B2, 2 B2 K 0, which will give you, which will give us -1 over B2 times negative K B2. So simply K. So that's K, and that's 4 minus K over 2. Now the question is, the goal is to find the range of K for which the system is going to be stable. And to have a stable system, we know that the first column of the Routh-Hurwitz, it must be all positive in this case, all positive. That means 4 minus K over 2 should be positive, and K should be positive as well. The first two values should be positive. So for a stable system, four minus K over 2 has to be greater than 0, and K has to be greater than 0. So one condition is this, that K has to be greater than 0. And the other condition is going to come from here, that 4 has to be greater than K over 2, or K over 2 has to be less than 4, which means that K has to be less than 8. So that means the range of K is 0, K8. Range range for which the system, range of K for which the system will be stable is 0, K8. K has to be between 0 and 8 in order for the system to be stable. So as I said, under these type of conditions, when we are trying to figure out the gain or whatever value of K, Routh-Hurwitz, it comes pretty handy. Yes. I'm sorry? K has to be greater than 0. If not, then this is going to become 0. Remember, the first column, the sign should not change. Either all the values should be positive or all the values should be negative. So since the first two values are positive, we want the third and fourth value should be positive as well in order for the system to be stable. Okay. All right. Case 4, repeated roots on the imaginary axis. This will result in an unstable system. However, Routh-Hurwitz method doesn't detect this form properly. So I'm not going to do this problem because it's just going to waste time. And as I said, Routh-Hurwitz does not work on this properly. So we are not going to touch this case using Routh-Hurwitz. You can always use roots function to see if the roots are on the right hand plane and the system is unstable. So we're going to go ahead and do example 6.9. Control system has a second order characteristic equation, s square plus as plus b. Determine the necessary and sufficient condition for the system to be stable. We're going to go ahead again and create Routh-Hurwitz array, s square, s to the power 0, 1, b, a, 0. And then this is going to be whatever we're going to call this, c or whatever. Since b is already there, I don't want to do b. So let's say this is c1. All right, one of the conditions, well, let's calculate c1 first. So c1 will simply be negative 1 over a, 1a b 0, which will give us 1 minus ab, 0 minus a times b divided by a. So that's simply going to be b. C1 is simply b. So in order for the system to be stable, the condition is very simple, that a and b both have to be greater than 0 in order for the first column to be all positive. And the last problem, let's do this. So we can have one complete lecture of chapter 6 that I can post. Control system has this characteristic equation. Determine the range of k for a stable system. Again, let's use Routh-Hurwitz method. So once again, in these cases, make sure you use Routh-Hurwitz. That's easy. You don't really have to ask me what method to be used. But if it is just, I'm asking to determine the stability, you don't really have to use Routh-Hurwitz method. Just calculate the roots and determine the stability of the system. Let's keep 1, k plus 1, 2, and 8. And then we have b2, b0 will be 0, and c2. This is going to be 0 because you don't have any column here. So b2 will be equal to negative 1 over 2, 1, 2, k plus 1, and 8. That's going to give us 2k plus 2 minus 8 over 2. So 2k, 2 minus 8 is negative 6. 2k minus 6 over 2, which will be k minus 3. This is k minus 3. And C2 will simply be 8. So C2 will be negative 1 over B2, 2 times 2B2 and 8, 0, which will give us 0 minus 8B2 divided by negative B2. So that's going to be 8. So in order for the system to be stable, then k minus 3 has to be greater than 0. Therefore, k has to be greater than 3. For a stable system, k minus 3 has to be greater than 0, which implies k has to be greater than And that's the end of this chapter.